This video is about binary search trees. Binary search trees are a special type of binary trees, and a binary tree in turn is either empty or contains some data together with two subtrees. A binary search tree, however, needs to obey an extra property, and that is all the data in the left subtree should be strictly less than the data in the root, which in turn should be strictly less than all the data in the right subtree. Here the function f is a helper function that takes as the first two arguments a minimum bound, a lower bound, and the second argument an upper bound. Okay, the typical operations on binary search trees are adding an element, checking for membership, and removing an element. Here x stands for one data element, and x's stands for a set. Now to add an element x to a set, I'm gonna pattern match on a few cases depending on what the set already contains. So the set could be empty, or it could branch. In the first case, it's clear what to do. We return the representation of a set with one element. In the second case, in order to maintain the invariant stated earlier, we need to further distinguish three other cases depending on whether x, the element we try to add, is smaller, equal, or greater than y, the element that is already at the root. When x is different from y, we just recurse. So I need to make the function recursive. Otherwise, if x is equal to y, that means that the element is already in the set, so there's nothing to do. To check for membership, we need to distinguish basically the same cases. If we bumped into an empty set, then x is not there. In these two cases, just as before, we recurse. We search in the left subtree or in the right subtree. And the last case corresponds to the situation where x equals y, so it is in the set. Some of these variables are not needed. Okay, I wrote a lot of code, so let's test a little bit. Okay, let's make a set out of a list by repeated application of add. We see that the repeated element 2 appears only once, and we also see that the numbers appear in strictly increasing order: 1, 2, 3, 4, 7, 8. Let's check for membership. Two is a member of this set. Five is not a member of this set. Okay, seems to work. So now let's go back to deletion. For deletion, again, we do something very similar. And distinguish the same four cases. The set is empty, there's nothing to do. If you remove an element from the empty set, the set remains empty. Now this last branch is reached when x equals y, so I don't really need to name this variable, and we need to remove x. The problem is that we are left with two trees, L and R, and we need to return 1, so it's not completely clear what to do. We can get around it like this. Suppose we divide further into one subcase where it happens that the right subtree is empty. Do we know what to do then? Yes, we do. We just return the left subtree. And in other situations, it's possible to reduce the case to the one above. So in other situations, we found the element we want to remove somewhere in the middle of the tree, but we only know how to deal with it if the element is somewhere at the bottom of the tree, more precisely where it does not have a right branch. So what we're gonna do is gonna change a little bit the tree such that we push down the element that we want to remove, and then repeat, we try again to remove x from it. So what do I mean by this pushing down? This pushing down is an operation usually called rotation, and the simplest way to explain what it does is to just implement it, because it's very easy to see the pattern of what's going on. So I'm gonna do what's called a left rotation, which takes a tree that looks like this and produces a tree that looks like this. So one that branches to the right gets transformed in one that branches on the left. Now I'm gonna put some variable names inside here, and I will append a number that says what is their order in this tree. So I have a tree here, which is the first one, some data, then another tree, then some other data, and the last tree. And then they come here in exactly the same order. Okay, there's one more parenthesis. First tree, second data, third tree, fourth data, last tree. So you see that the invariant is preserved because things coming from left to right are in the same order. In other cases, we are not supposed to apply rotation. And now let's try to test this. Line 28. Oh. Okay. Let's define the set. And now let's try to delete something from it. Let's say that we want to delete number 2, which you see is here, and the right subtree is not empty, so it will need to apply also rotation. So we started with 1, 2, 3, 4, 7, 8, and we ended up with 1, 3, 4, 7, 8. So the removal worked. Okay, so that's binary search trees. When should you use it? Well, you should binary search trees when you need persistency. You see that here, when we add something to a set, the old one doesn't disappear. So we can just add, say, 10 to the set x's. Now we have the set x's and the set y's that are somewhat similar, and they will be sharing memory, a lot of memory for this representation. The second situation where you should use binary search trees for representing sets is when the problem you're trying to solve somehow involves the order of the data, total order on the data. So for example, if you're talking about sets of intervals, and you want to see which intervals contain a certain point, then that would involve order, because the way you define that the point is inside an interval is by saying one number is bigger than another number. So if you want to have a set of intervals, then maybe you should consider a binary search tree. Some problems are that it's not as fast as a hash table. It uses a little bit more memory because of these pointers to subtrees. And of course, the biggest problem with the implementation we have here is that the trees are not balanced. What does that mean? Well, it means that if I try to construct a tree out of a sorted list, for example, what I get back is something that looks very much like the list itself. This tree is always branching towards the left, so it's a very tall and skinny tree, which is not good, because then if I'm gonna try to ask, for example, if 9 is in this set, or sorry, if 1 is in this set, then it will always go down all these 9 levels to find 1. And if I have a sequence of operations, is 1, there is 1, there is 1, there is going to be really slow. So there has to be on top of what I said, what I implemented here, there has to be some mechanism for balancing the tree. But this I will put in a subsequent video. That's it.